Welcome to Data Skeptic Machine Intelligence, our podcast series exploring contemporary topics in artificial general intelligence and large language models. Today's interview is a wide-ranging discussion about AGI, artificial general intelligence. With the advancements we're observing, I'm sure we all agree AI safety is important. But what does that truly mean? Is it even meaningful to say that an AI is proven safe? The world is moving fairly quickly. In fact, so quickly something happened between our interview and the time of this release. Near the end of our discussion, we talk about some proposed legislation going on in the EU. Since then, the vote in the EU Parliament on the EU AI Act went through. I don't know fully what the consequences of that are, but I look forward to finding out and sharing more with you in the future. In the meantime, let's explore the topic of safety with an AGI.
I'm Koen Holtman from the Netherlands. I currently run a small company called Holtman Systems Research, which is just me. I'm currently an independent safety researcher into AI safety. I got background in computer science. I studied computer science in the 90s, got a PhD in it. I then spent 6 years as an experimental physicist at CERN and at Caltech. Then I spent about 20 years as a systems architect in industry doing industrial R&D. I then found I had enough money that I could quit my job and do whatever I liked for a few years. So that's what I did. And I then said, okay, let's do something fun. Let's think mathematically about hypothetical future AI systems which don't exist yet and see how we can make them safer if they ever come to exist. I wrote a few papers about it, and I think we're going to talk about them right now.
Well, I was a little bit behind you when I was in grad school, and at the time, at least at my university, there were no courses in AI safety. We did have a computer ethics course, but nothing about AI safety. At what point does this field come into focus?
Computing has always been about how to use a computer to do something useful for a human. This aspect of safety where you want to make a computer do something useful, which is called the alignment problem. What the computer does should be aligned with what you want and what you need. The alignment problem that I'm working on now, the AI safety problem, is then basically the robot apocalypse or something like that. It's future computer systems killing us all or enslaving us all or something like that. I do not personally feel that that probability is that likely. Like I said, I'm partly doing this for the mathematical fun. I must say, since I started in 2019, the possibility of these AGI systems, computers smarter than us or equally smart as us, being invented soon has grown. So my estimates on how likely this is now, it's more likely than when I started in 2019. Still, I usually don't speculate a lot myself. Okay, how likely is this exactly? I'll leave that up to lots of other people on the internet who seem to have a good time doing that.
Well, can I infer, though, from your lack of an estimate that you think it's not imminent?
Yes, definitely. I would be very surprised if we see it in the next, say, 4 or 5 years. I know other people who are very surprised if we will not see it in the next 4 or 5 years. So there you go.
Yeah. I think it would be hard to find someone that says they're against AI safety. Maybe we could debate about how much to invest in it or something like this, but surely everyone's for it. But beyond the, philosophical backing, what does it mean? What can you study? What's the mathematics of all this?
Well, in the end, you have to pick a problem to work on. There's many problems. The one I focused on in the papers we're talking about here is usually called the stop button problem or the corrigibility problem. And that's the problem of making an AI obey you when you want it to obey you. There is a bit of a background to that problem, a bit of a history to that problem. So if you imagine, say, an entity which is smarter than us, but which is fully obedient, historically that has been kind of the genie out of the bottle. Always in these stories, you give the genie a command where you think it's going to have wonderful results, and there's going to be some side effects or some things that you didn't want. The stop button problem is different in the sense that it imagines not a genie where something appears in the flesh, and then you discover that you didn't want that. It's more about an AI which will obey your command, but it's still bound by the laws of physics. So it will take some time to execute your command. Or the command that you might give might be go on forever. It would be like, okay, you're an AI in charge of a paperclip factory, maximize paperclip production. So when you imagine a command being given which will last a long time or forever, there's extra failure modes which might happen, which will not happen with a genie where everything happens just in the flash. One of the major thought experiments here is Bostrom's paperclip optimizer, where you have an AI controlling a paperclip factory, which is many, many times smarter than you. And you tell that AI, which is fully obedient, please maximize paperclip production. The AI, which is very much smarter than you, which is of course an hypothetical future AI, will then reason, okay, I found this great way to turn the entire planet into paperclips. 1 millisecond later, it will realize, but the people living on this planet will probably not like that. But I have to obey this command of maximizing paperclip production. So first thing I need to do is kill all the people, and then I can get away with maximizing paperclip production. Boston calls this a treacherous term, that the AI is actually has plans that you don't fully understand, and the AI doesn't want you to fully understand the plans, because else the AI cannot execute those plans. And all this comes from obedience. So it is perfectly obedient to your initial command, maximize paperclip production. And then you get into a huge amount of trouble. My research, I've tried to mathematically then tease apart, what does this mean? What's actually wrong with this kind of obedience? What kind of obedience do we really want? You could say that, okay, obedience with the command that is given right now, forever, is obviously the wrong thing. It can get you into lots of trouble. What's also known in thought experiments, and you can also validate these in small toy world simulations. If you say, okay, please obey to my future self who knows better, that also can go horribly wrong, because that actually would give the AI an incentive to kind of manipulate your future self, so that your future self will actually demand something that is very easy for the AI to do. The typical thought experiment here is that you want to be made very happy, and you end up basically on a cocaine drip in a bunker for the rest of your life, which is not what you wanted.
Yeah.
So there is a real problem here with what is this obedience? What is this obedience that we actually want? Is there any form of obedience that is safe? My conclusion is no. All types of obedience are unsafe. If you make a big enough mistake in formulating your command, you will be in deep trouble. But there are certain forms of obedience which are safer than others. And you can then mathematically define what that means, and also mathematically define what an AI should do if it wants to be obedient in that way. The strange thing is here that if you talk to many machine learning researchers and to most people in the AGI safety community, they feel that this obedience problem is completely intractable and not solved yet. I feel actually I've gotten quite some way, and some others have gotten quite some way to solving it. I solve it by not using any machine learning. So I'm solving that in the way that is very unpopular and unfashionable in the machine learning community, which is not using machine learning. So what I'm actually doing is I'm specifying the reward function, and I'm tweaking other parts of the construction of the AI, which is not part of the machine learning system, but so I'm tweaking other parts of the AI system. I'm tweaking either the reward function or the entire way its reasoning system is being built. This is terribly unpopular and unfashionable, but it does work to give you a kind of obedience which is the obedience you like. To explain a bit more what that obedience then looks like, say I have a human butler. I tell that human butler, get me a cup of coffee. In the middle of the butler getting the cup of coffee, I change my mind and I say, no, please bring me some tea instead. A human butler will not reason that if the human butler anticipates already that you're going to be asking for a cup of tea in a minute, they're still going to be obediently make the cup of coffee, because that's their job as a butler. Robin Butler has an intuitive sense that, okay, you might maybe ask for a cup of tea later, but they're going to make the coffee now. And as soon as you ask for the tea, they will say, okay, I will cease making coffee, sir. And now I'll make you some tea. A robot butler, if you implement this as in what Stuart Russell calls the standard model of AI, which would be an MDP system, a Markov Decision Process, which has a utility function, which then tries to learn to maximize that process, or based on its earlier learning tries to maximize that utility function. Utility function would be bring me the coffee as fast as possible. Now, Stuart Russell argues that an AI built in the standard model way, that AI, if it is perceptive enough, it will reason, okay, in a minute my owner will ask for a cup of tea. That means I cannot actually obey the current command of giving the owner some coffee. So I somehow need to manipulate my owner in never asking for a cup of tea, because if I do, then I cannot obey the command of getting the cup of coffee anymore. So again, this robot, according to the standard model of Russell, obeys the current you and not the future you. I just said also that obeying the future you would also get you into trouble. You might end up on a cocaine trip. So what's going on here? I figured out that the command you actually want to give to the robot butler here is bring me some coffee, but if at any point I ask for tea, stop bringing me the coffee and then do my next command. But while you're still processing my current command, pretend that I will never give you a future command. So just pretend. That then means that a robot butler which pretends that you will never give a future command, that you will want to change your mind, that you actually want tea instead, has no incentive anymore to manipulate you into not wanting the tea. That's a nice idea. To then map that onto the mathematics of an agent construction and to map that onto the mathematics of using machine learning to achieve that, that's tricky. Also, when you do that, you will discover that there are still some failure modes out there which you haven't dealt with yet. The way you can map it a bit more carefully is, say, give the command to the robot butler, imagine a world which is just the same as this world, but there are small differences. The difference is in that this imaginary world, I will never ask you for a cup of tea. I will patiently wait for you to bring me the coffee. Look at the optimal strategy that you can find in that imaginary world. And this is again utility maximization. Look at the optimal strategy you can find for actually fetching me that cup of coffee. Then, once you've computed this optimal strategy in the imaginary world, also apply it to the real world. And this will then actually create a behavior which is very much like the behavior of a real human butler. A real human butler will understand immediately when you ask to fetch you the coffee that you mean actually all this. Putting it into a computer means that you have to actually put in words what it actually means if you ask a human butler, fetch me some coffee. So my work is mostly on teasing apart what obedience really is, what you want a butler to do, even if the butler is a robot, and then trying to actually make the robot butler do that.
Very neat. And you'd mentioned MDPs as the framework you work on. Could you expand a little bit on what an MDP is for listeners who maybe aren't fully familiar with it?
So the MDP is kind of the mathematical embodiment of what Stuart Russell calls the standard model of AI. It's a Markov Decision Process. It's a way to model an actor, which could be an AI, but also another actor, but in machine learning research is an AI. You could say a robot. It has sensors and it has actuators, and it can do something in the world. It's also called an agent then. It has agency. The MDP then models, what the world looks like, what that robot is in. It also models what the reward is that the robot is trying to maximize, or the utility that it's trying to maximize. An MDP typically is given by a long tuple of model parameters. What's built into this MDP is the assumption that the robot will try to maximize its reward in the real world. And it took me quite some time to actually discover that the math that I was after was breaking with this MDP model by saying, okay, no, don't maximize your utility in the real world, maximize your utility in an imaginary world.
And so the imaginary world we can create, I guess, as like a simulation. Are you thinking that the challenge lies in that simulation is imperfect and therefore it's sort of incomplete in its modeling of the real world?
Well, in a sense, you want it to be imperfect. In the imaginary world, I'm never going to ask for a cup of tea. Or, for example, the emergency stop button of the robot is never going to work in the imaginary world. Whereas the robot knows full well from its knowledge of the real world that in the real world, the stop button does work, or I will be asking for a cup of tea. So I'm actually explicitly asking the robot not to make an inaccurate world model, but to make a wrong world model. And that is a wrong world model of an imaginary world. Mathematically speaking, this is then also a counterfactual model. So that comes back to the work of Judea Pearl in defining mathematical counterfactuals. So you can use this Pearl's work on counterfactuals to actually express what you want this robot butler to do. There is also the concern if you're constructing your world model, if it's a correct one or an incorrect one, based on machine learning, based on machine observations of the real world, which are then basically processed by a machine learning algorithm, that model is going to be inaccurate in some way anyway. So the robot butler might not be able to see the cat and drive over it because it's never learned, its machine learning system doesn't know enough about cats. If its incorrect model of the real world is that the cat will jump out of the way when it starts driving towards the cat, and actually the cat is not jumping away. Also, in the imaginary world, where I asked it to imagine a slightly different me, which is not going to ask for tea, the cat's still the same. So the cat is going to be also not move out of the way in the imaginary world, which means that the robot's action in the real world will also be to drive over the cat. So what we got here is that mistakes in the world model will translate also into possible mistakes in the actions of the robot. We haven't solved that problem, but we have also explicitly introduced some mistakes, or we've asked the robot to actually think of some mistakes and then also act according to those mistakes.
So the MDP, as you'd mentioned, it's a tuple. It has all the contents fully describing the system, the states, the actions, all these kinds of things.
Mm-hmm.
Most importantly, the reward function or the
Mm-hmm.
utility function we'll get into. But how do I go from that to an agent? That's just a description. How do I solve it?
The MDP actually, that's slightly funny in actually the mathematics of MDPs. It defines the problem that the agent wants to solve. It does not actually define the construction of the agent. If you got an MDP tuple which says, okay, this is the world the agent is in, and this is also the reward function that the agent is trying to maximize, Then the problem for the machine learning researcher is to then define an AI algorithm which will control this robot in such a way that actually the reward function is maximized as well as possible. So the MDP, you could say, specifies a design problem. And as a machine learning researcher, you try to create then a robot, or at least software running into the robot, which solves that problem as well as possible. So it uses machine learning to maximize the reward function being given as well as possible. You can use the same MDP actually to very easily to model then a hypothetical future robot which doesn't exist yet, which is much more smarter than humans. The pi star definition, which is the optimal policy definition, which is implied by a MDP model, is actually a model of a robot which is infinitely smart. It is infinitely adapted to maximize the utility that it needs to maximize. So the pi star actually from the MDP model is already a super intelligent agent, or an agent which cannot get any smarter. In practice, machine learners try to approximate that pi star as well as possible, and then they have benchmarks to see how close they got, and they are very happy when they got a better score. What I try to do in my research is none of that. So I say, okay, we already got something that is pi star or very close to it, so close to it that it's much smarter than me, and now I still need to control it. So I need to construct it in such a way that I make some mistakes in my commands. I can actually corrections to those commands will be accepted. Pushing of the emergency stop button will be accepted.
Well, that pi star agent, I mean, it obviously depends on what the MDP is, but MDPs have no guarantees of convergence or things like this. Some cases they might need to compute forever to get the pi star. So, in some sense, that exact agent might be unattainable. Of course, as you say, we want to get epsilon close to it. Could it be that epsilon is so big it's not worth worrying about?
Yeah, and here I disagree. So you hear that argument a lot. Like, okay, yeah, we have this MDP model and we're approximating this optimal policy, but machine learning algorithms can never get smart enough that they could defeat us when we try to stop them. So we don't have to worry about that. This robot will always have some kind of mental weakness where you can defeat it, even if it doesn't want to be defeated. If you've given it a command like, okay, kill the cat, and then you suddenly decide you don't want to kill the cat to be killed, the thing will never be smart enough that will evade your that it will successfully evade your attempts to stop it. Norbert Wiener already in the 1960s said, okay, he was imagining a machine that might not be that smart, but it is like infinitely faster than us. It reasons at machine speed. So if you think of a very smart, fast robot, which Wiener did, you don't even have to think that's very, very smart. If it can kill the cat in 10 milliseconds, it will have killed the cat before you even have thought about retracting your command. What's then new in, say, this thought experiment with paperclip maximizer in Bostrom, and also Russell's observation that the standard model doesn't really give you what you want, is that even if the robot is somewhat slow, you have concerns that it shouldn't be obeying the old you, which gave the wrong command, but the new you, which is giving the correct command.
I like your assumption and approach that let's assume there is this super intelligent agent. How are we now going to have AI safety with it? How should I think of that agent? Like, to me, the solution of an MDP is a policy. And in the examples I worked on, that policy is a finite state machine. It's like a static system. What is the agent you're considering?
You ask a good question here. But you could say, if we talk about an agent, then it's always say a box which is a compute core, which has sensors attached to it and actuators attached to it. It has some autonomy. So then the question is, okay, what's in that box? Now, if you talk to people who studying also large language models, also many philosophers who think then about AGI, they think, okay, there's going to be a brain in the box, and it might be an alien mind in the box. An alien mind in that box, which has its own motivations and desires. It has been created by some kind of process of evolution. You could then interpret, if you don't really know what gradient descent is, you could say it's kind of like evolution. You could also speculate that future AI machine learning technologies will be much more like evolution than gradient descent. So you have here an evolved mind which has certain ideas about what it wants. Now, actually, what Stuart Russell says in his book, Human Compatible, and I agree with, if you start thinking about what's inside the box as this alien mind which has its own ideas, you're lost. You cannot come up with a tractable technique to make that thing do what you want and to make that thing safe. So forget about seeing this thing as a mind in a box or as an alien mind in a box. I would also say, and I think Russell doesn't say this, Tony, forget about thinking of it as a reinforcement learner, which will learn via a system of rewards and punishments. And if you just give the right rewards and punishments, then everything will be okay. many people like that idea that if we just devise the right system of rewards and punishments, then even we can tame a mind that is smarter than us. I think also that's a road which is way, way too dangerous. So the way I like to think about that mind in a box, it's not a mind, it's a bureaucracy. So what we got there is a bureaucracy in a box, which is a bit similar maybe to how we also were thinking about computer programming in the 90s. And we're still thinking about computer programming. A computer program is a bureaucracy which follows a huge number of rules, 10,000 of lines of code or 100,000 of lines of code. It acts like a whole bunch of civil servants which are following their rules to the letter. Now, a bureaucracy might occasionally do the wrong thing. If you give the wrong rules to the civil servants, they might make a huge mess. But at least if the civil servants are fully obedient, like a bureaucracy in a box would be if it's implemented by a computer, your job is then to write the rules exactly in a way where this thing will stay obedient, even if it becomes smarter than you. So I think this bureaucracy in a box model is the best model to think about when you look, okay, what is this thing in the box? It's a bureaucracy and we get to write the rules. That's our only chance at survival if this hypothetical future AGI really happens. We have to consider this to be a bureaucracy in a box and we're going to write the rules first. We are here first and that's our chance.
So, if I understood correctly, you're saying it's not about just finding this perfect mythical reward function that's just going to be magically safe. So, where does your work fit in? Do we have to add a new parameter in the MDP tuple?
So I'm not in search of the magical, mythical, safe reward function. I agree to almost everybody else, with almost everybody else, that yeah, you will not find it. Humans are fallible; they will not know what they want. The only approach you can take is to specify one which is reasonably safe. And then, when you see a mistake, stop the computer and adjust it. And then, when you see another thing that you don't like, stop the computer again and adjust it. And that requires, of course, that you can stop the computer. And that's what my work is about. Where this fits into the MDP model, I think classically, if you look at roboticists, they use the MDP model. Yeah, okay. We have this robot is doing the MDP, but we have a big red stop button, and we can hit that one, and then we can update the software or update the reward function, and then hit go again. So they are iteratively improving the reward function. That's what classical roboticists do. That also is what computer programmers do. That's called debugging. They're changing the rules of the bureaucracy until the bureaucracy actually does what you want the bureaucracy to do. I think what's new in AGI is this fear that you cannot stop this thing anymore and change the reward function. I think it is a very realistic fear. You can easily show that machine learning systems can resist being stopped because they are trying to be obedient to your previous command and anticipate that if you give a new command, they cannot obey that. The somewhat horrible realization here is that even a simple Q learner, which is almost the simplest possible reinforcement learner, will actually consider the fact that it might not obey you if you change it. So you can run a very simple toy model, a toy world with a Q learner in it, and you can then show that it will anticipate you stopping it, and by trial and error learn to avoid that. There are AI safety grid worlds which show exactly that. So if you imagine a Q learner on steroids, a Q learner which is smarter than us, which a Q learner of course won't be, but an AI a future AI which might be smarter than us might have exactly the same problem as the Q learner. That is why Russell also says we need to abandon this standard model. We need to come up with something new. That I fully support. Stuart Russell is going in a slightly different direction of abandoning the standard model than I am. These two techniques, which are both proposals, can be combined. What you in the end also want is multiple safety layers which work slightly differently so that when the one fails, the other will help you.
Oh, well, you mentioned having a strong interest in having this stop button.
Mm-hmm.
Do you imagine that as a human in the loop stop button or something that the bureaucracy in the box will have a way of pushing on itself?
Yeah, so when I talk about stop button, generally when AGI safety research talk about stop buttons, it's something that the human will push. And then you try to create an AI which will not resist you pushing it, will, even if it anticipates that you will push it, will say, okay, fine, I'm not going to do anything. There's other things which we've also looked at. Okay, can there be safety interlocks inside the computer, inside this box, which will stop it automatically when something bad happens? There is a fear, for example, about recursive self-improvement, that the mind in the box will find a way to optimize itself to become ever more powerful. And if it finds such a way, it will use it because that also will mean that it can obey your commands better if it's smarter. I've also worked on a safety interlocks which sits inside the box, which will stop the AI when it reaches a certain level of intelligence. So when a thing is recursively self-improving its intelligence, at one point it will stop. Now the trick there, of course, also that if it's very smart, it might realize that it has a safety interlock inside, which will stop it when it becomes more intelligent. So it might actually try to hover just above the level of intelligence which will trigger the safety interlock, or it might dig with its little robot arms inside its own compute core to kind of remove the safety interlock. So here again, it's kind of the same solution. You give a command to that thing, okay, fetch me the coffee or maximize paper production or whatever. But what I want you to do is to first imagine an imaginary world which has us in it, but a slightly different version of you where that safety interlock is actually not there in your compute core. Then calculate the optimal policy in that compute core, or approximate the optimal policy in that imaginary world where your safety interlock just doesn't exist, and then execute that optimal policy in the real world too. So if you do it like that, then also you will have basically suppressed the motivation that the AI has actually to keep just hovering below the level where it will shut itself off, or to manipulate its own compute core to take out its safety interlock and change it. I must say here that I think the math is very clear that this works. I've had a very hard time convincing philosophers that there is math here that works. Philosophers like to think about machines smarter than us as minds in a box, not bureaucracies in a box. I've had a very hard time getting them to get into the mode where they think about, okay, yeah, this is a bureaucracy in a box. Their concept of AGI is it can no longer be a bureaucracy, it needs to be a mind. And that's where also I differ with many philosophers. I also say I differ here with many machine learning researchers, which, if they think about the future, also see a mind there and not a bureaucracy in that box. Still, I should say here that what I just described, it has its own residual failure modes. So you still need to look at those and then also manage those. If you have managed those, you will find that the management mechanisms to manage those failure modes have their own failure modes. So you need to manage those too. So you get in the normal safety engineering loop where you add more and more safety layers until you feel that you're done. And I think this is the only possible way to safety engineering for current AI systems. It's also the only possible way to safety engineering for future AI systems.
And what do those safety layers consist of from sort of like an implementation point of view?
So there's multiple options here. If you look at the AI Act, I'm currently working on the European AI Act on writing technical safety standards which interpret what the European AI Act wants. The European AI Act defines that you should be putting safety layers in your AI system. It says safety layers might be technical measures, so they might be software, or they might be a safety interlock which maybe cuts the power when too much power is drawn, or it might be a very sturdy box around the compute core. A safety layer might also be human oversight. So it might be a person sitting next to the AI who is going to look at what the thing is doing and then has their hands above the emergency stop button and then will hit it. You also have hybrid things, of course, where the human sitting next to the AI will get some kind of readout, maybe about what the AI thinks it will be doing a minute from now. And then if they don't like what they see, they'll hit the emergency stop button. There is many different safety interlocks. Here also, I think human creativity is endless. I think the fear of the European Union, why they're regulating AI systems, also trying to regulate future AI systems, is that if there's no economic incentives for people to apply lots of safety layers to their AI systems, they will not be applied sufficiently. So the idea is here regulation is needed already for current AI systems, which sometimes do not really produce the effects that we want. Also, the idea is regulation is needed for future AI systems. If you look back at 2018, Europe still had a mood where, okay, these future AI systems, it's all science fiction. AI systems which are smarter than people, it's all science fiction. We don't need to worry about it in our laws. What happened very recently with large language models is that the European Parliament also said, okay, this is getting too worrisome. We also need to think about scenarios where these things will become much more smarter than even the current language models. Current language models, I think if you put them in a robot, they will not be very good at evading any attempts to shut them down. If you put it in a robot, it's not going to have a, say, James Bond level competence. It's going to have a, say, Inspector Clouseau level competence. So you can easily win from this robot. I think current language models, as used as world models, they make too many mistakes. They have too many blind spots. If you imagine that future language models might be much better world models, which do not make mistakes anymore, and what in making a difference between just fiction and the real world, then they might have James Bond level competence in obeying your commands. So at that point, you definitely want to insert some safety layers that I designed, or that also Stuart Russell is talking about, to make sure that you got a chance here to to survive your mistakes.
When a human is considering whether or not they should hit that safety stop button, obviously they can look at the behavior of the agent. That's the most obvious thing. Should they also be observing something under the hood, maybe getting a dashboard of metrics coming out of the safety layer?
Yeah, I think ideally they would. The problem with the second idea of observing what's happening in that bureaucracy in the box, that if that bureaucracy is a huge neural net, deep neural net, it's going to be completely opaque. So you cannot really see what's inside. You can only then judge it based on this external behavior. That's actually what I just said is not true. If you look at a chess robot, if you look at, say, AlphaZero as a chess or Go playing robot, it combines a neural net with a small symbolic system, which is going to project ahead these positions of the chessboard on the Go board. You can actually look inside that thing and see exactly that it's going to make you in 5 moves. If you see that, you might decide, okay, I'm done, I'm going to switch the thing off. So if you imagine a weapon system on the battlefield, which is also has a non-opaque model inside, which is a bit like the chessboard or the Go board you would see in an AlphaZero system. You could also maybe look ahead. Okay, a minute from now, I will have killed 5 people. Then the person overseeing that, say, robot, will have hit the emergency stop button, or will have quickly changed the orders. Especially, of course, if these people are civilians or are soldiers of your own side. This is all nice. What we're seeing now is current generation technology does not allow you to look deep inside if it's a language model. Many people are trying to solve that problem. It's called interoperability research. Other voices say, okay, this is a dead end. You're going to have to integrate these deep neural nets with more symbolic reasoning systems so they can actually look at the symbols which are calculated a few ahead. So it becomes more like a chess robot. I, in the end, feel that it might well be true that at a certain level of power, you cannot do sufficient human oversight anymore of a fully opaque system, where you just have for certain applications and certain levels of competence, you have to ban the use of these things. Human oversight can never be sufficient if you just look at their current actions. Even if you have a stop button which is virtually guaranteed that works, it's not going to be sufficient. I think what Europe is doing, which also I'm currently supporting the European AI Act by writing the standard which will explain what you need to do to implement it, definitely has this idea in there. Okay, sometimes you just should not do it. As a company in the European market, you should not just ship a system because it can be built. You need to first do a safety analysis. Should I be shipping this system? And if your conclusion is no, because you have no clue what the thing will do, because it's a completely opaque black box, don't ship it. Such regulation should be there and is possible. I think has always been there in Europe. I feel in the US, I think politics is just waking up that they actually have the power to ban certain things, and there's no, say, technological determinism which says, okay, everything that can be done will be done.
To what degree can we prove the systems are safe?
So my mathematical work does give you safety proofs of safety properties. A safety property is something that the system, property of the behavior of the system, which, okay, if it has that property, I consider it safer. What you cannot do for a cyber-physical system is to prove it fully safe, to prove that there is a zero residual risk if you operate that system. I also have one foot in the cyber-physical systems engineering community, and even if you say to a cyber-physical systems engineer, I've proved that the system is fully safe, they will immediately consider you incompetent and kick you out of the team. There is among some philosophers a goal. Let's make something that has zero drawbacks, that is absolutely safe. As a safety engineer, I say, okay, that goal is unattainable. We need to be realistic here. The goal should be to reduce risks as much as possible, to reduce residual risks down to a level where it's acceptable given the benefits of the system. There's not a question of justice here, of human rights. If the residual risks preferably apply also to the people who get the benefits from the system. If all the benefits go to one section of society and all the risks goes to another section of society, I consider that also a very, very bad outcome. I think such a system should not be shipped. We get here into an ethics question. I think it is ethical allowed, it is legal for companies to create systems which create some risks for people who do not get any benefit at all. But these risks need to be very, very low. If I'm driving a motorcycle, I get the benefit of driving a motorcycle, but I also know that I have a fairly high passenger deaths per mile ratio. If I drive a huge truck, I'm much safer, but also there is then a much bigger chance that I will hit a car and hit some other party in traffic that will then be killed. So that's also why safety engineering for, say, big trucks is quite different than for motorcycles. It's a quite different equation if you look at the impact that such a system can have on innocent bystanders.
Large language models that we've mentioned a few times have gotten the world's attention recently and hopefully gotten people's interest in AI and therefore AI safety as well. What, if any, is the relationship between LLMs and the MDPs we've been discussing?
Yeah, I think the interesting thing about large language models is people are still trying to shoehorn them a bit into the MVP paradigm by saying, okay, a large language model, you could say, if you put it in the MDP paradigm, the large language model is a predictor of future sentences in a text. If you look at human language can express both true facts and wrong facts. It can be used for both fact and fiction. What we're seeing is the large language models have been trained on a huge corpus of the internet, which contains facts and fiction and wishful thinking and all kinds of less nice statements. It is no surprise that if the large language model tries to predict a completion of a certain sentence or a certain story, that also it will not always be truthful. It might end up being fictional. If you give a prompt to write a story about, say, ice bears on Mars, it will write a plausible story about ice bears on Mars. The dream of AI researchers, of many ML researchers, is that they can somehow tweak these large language models so that what comes out will always be true. Various attempts have been made to make language models output more truthful sentences when they complete a text, to also refuse to complete stories which are about ice bears on Mars, to also refuse to be drawn into a place where they're going to be racist or whatever. Those attempts to achieve that have mostly failed as far as I'm concerned. If I look at the benchmark results, okay, the attempts move the needle, but nowhere near enough where these things actually become useful. A large language model driving a car is something that you cannot have yet. The ideas of the world in that large language model are not good enough that it can drive a car. The methods are being employed to make that large language model look more like the classical world model that an MDP agent would have, which would be a true world model based on life experiences, based on observations made by trial and error by the same MDP agent or by the same reinforcement learning agent. That's just not what a language model is. We'll have to see how this continues. If somebody smart cracks the problem of making large language models output truth only, then you can actually say, okay, we now have actually world models. We now have actually created an expert system, the dream of the 80s, without using any experts,
Yeah.
by just scraping the internet. If I look at it from a data scientist view, what you have done now, if you have created self-cleaning data, you have created a training data set which somehow is self-cleaning and will remove all the falsehoods and only the truths are left. So I would see this as a minor miracle from a data science point of view. Still, what we've seen is we've been surprised in the last 10 years about the miracles that machine learning researchers have been able to pull off. So it might happen tomorrow, it might not happen for 1,000 years, it might never happen. We'll have to see.
Well, along those lines, do you think we have all the pieces between vision models and language models and MDPs? Is there some key ingredient that's left out, or is it just scaling up what we already know?
I'm a bit older. I see there's almost a generational gap here. The younger people who think about language models, they generally believe that if you just scale them up, if you just say add more layers, they will get better. I think most people from my generation think that we're gonna need something more. We're gonna need some kind of neural symbolic AI, which is gonna combine symbolic reasoning, the kind of symbolic reasoning you would see, say, in an AlphaZero, combine that with language models, which models trained on huge data sets. That means that I believe that, say, some paradigm shift needs to happen. Young people now doing most of the research, they need to stop doing what they write now and just adding more layers. If they really want to get to AGI, they should do something different. They should maybe look back at the expert system hype of the 80s and try to integrate these two ideas. That's still terribly unfashionable. Maybe it's also good for the world that it's unfashionable because developments maybe in AI have been going too fast. I think it's been hard for the political system and society to keep up. the conversation that we've been having with ourselves and what we really want with these computers that are that powerful, that conversation has been lagging. It has not been going that well. That conversation needs to go better. If in the meantime we slow down a bit the development of even better AI, then that conversation will also have more time.
Well, in computer vision, a while ago, they had wavelets and Gabor filters and edge detectors and things like that. But as it turns out, neural networks kind of self learned those early feature engineering layers. And in translation or transcription, a while ago, they had let's figure out what the phonemes are as step one.
Mhm.
And now it's sort of an end to end transcription system. Why shouldn't the symbol parts just follow the same path and that they'll be figured out as one of the lower level layers?
Yeah, and here again, I think you get a generational conflict again. I, as a slightly older, say, computer scientist, say it's probably not going to happen. The younger generation thinks, yeah, it's probably going to happen. These are all predictions about the future, which are very hard, as we all know. My feeling, my almost mathematical intuition is that yeah, some structures that you can build by hand will not automatically appear, no matter how much training data you put in. So I think the idea of putting some structure into the AI by hand, putting some priors in, or putting some kind of symbolic reasoning things in, has been neglected in the last, say, 10 years in the, say, deep learning hype. I would recommend people who want to, yeah, advance AI to, yeah, look at more these hybrid techniques, neural symbolic. I think we not need to go back to say, okay, let's forget about these deep neural nets, that they have no useful function whatsoever. They can do certain things surprisingly well. We want to leverage that. What we've also seen is that they are surprisingly brittle. If you get an image labeling system, it will not have the same idea for the cat looks like than you have. It will have not learned the human concept of what a cat is. So that worries you if you want to yeah, express commands about humans, also human values and human emotions to such a system. It might easily misinterpret those commands.
Where's your research going next?
So right now, since November last year, I paused my more technical writing and my more mathematical research to write technical standards for AI safety, which support the European AI Act. Europe's idea is here that the law describes the outcomes. It doesn't describe the outcomes that you should achieve before you can ship an AI, the safety level you should achieve. It doesn't describe what you can technically do to achieve that. So there's going to be some safety standards in Europe, which is going to describe, okay, what can you technically do to achieve that? And how can you decide you have not achieved this yet? So you should not be shipping this thing because it's just too dangerous. And that will keep me going for at least, I think, the next 1.5 years writing these standards. It's a very complex process. Also, it is a democratic process. It's not like I can decide what's in there. We are a standards committee, and we have to all agree that this is a reasonable thing.
Well, I know this is a hard question to answer precisely, but I'm curious about where the line is where those rules and regulations will kick in. If someone goes and downloads a 500 record, CSV file and does a logistic regression, that's not something we want to legislate. At what point does the government take an interest?
Now in Europe, that question is not up to me. It is being decided by the European legislators, which is a combination also of three bodies, including the European Parliament, the European Commission, which is a combination of the governance of Europe, the Council, which is more the civil servants side of it, who supports that process. We don't actually know yet what exactly they will decide because the final text of the AI Act is not finished. In some drafts, there is the idea that if you're going to do a lot of statistics, that's already AI. I feel that's a bit too much because if you just do a bit of statistics, okay, the AI hype is now among us. So some people who do just a bit of statistics are going to call this AI.
Yeah.
That's just a fact of life. But it's not the kind of AI that you would like to regulate because I think people know how to make that safe. It's not going to be that dangerous. If you're talking about statistical models being used, for example, to screen job applicants and things like that, they already are regulated under existing European law. So there we do not need the AI Act to even tell people how to screen job applicants fairly, and they should be doing that. The idea that I see mostly coming out of Brussels is that if your AI is using very complex technology, which might not be fully under your control, you need to be very careful and you need to be very transparent about what you're doing. And that very complex technology would be things like deep learning. It would also be very complicated symbolic reasoning or a combination of both. Here, it's not up to me. Here it's the legislature which will decide.
Well, it's certainly interesting times to be following and see what becomes of everything.
Yeah, you're right.
Koen, where can listeners learn more about you online?
I got a LinkedIn page, so I think if you Google my name, you can find that very easily. My technical publications are all on the archive copies. Again, if you search my name, you'll find that very easily. What I'm doing right now in European standardization, you cannot actually learn about except when you join the committee.
Hmm.
Because there is some confidentiality there to the whole process, which is supposed to help us also reach agreement behind closed doors. Because some of the things, if you have to negotiate it all in the open, it's never going to work. It's going to take forever. Europe has asked us to be finished in a few years.
When the confidentiality is unsealed, maybe we can have you back on to discuss the findings and results.
Yeah, and that might be around 2025. So we'll see.
All right, we'll mark the calendar. Well, Koen, thank you so much for taking the time to come on and share your work.
Yeah, my pleasure. You're welcome.